Hello everybody, this is Skill 9, one-to-one functions with inverses. Okay, so let's start with reminding ourselves what a function is. So a function is a relation that maps each element of the domain to exactly one element of the range. Okay, so each of our x values are going to go to only one y value. Okay, if there was an x value that went to two different y values, it would not be a function. So if I look at the ordered pair 2, -3, then there can be no other point that can have an x coordinate of 2. However, it is possible for another point on the graph of f of x to have a y coordinate of -3. So if I look at 2, -3, and 5, -3, both of those points would still be a function. A one-to-one function, however, is where each x value is paired with only one y value and vice versa. Okay? So when we look at the 2, -3 and the 5, -3, if they were both on the graph of f of x, while it would be a function, it would not be a one-to-one function because both of those x values, 2 and 5, have the same y value. So it's not one-to-one. So think of a one-to-one function as being like boyfriend-girlfriend or partner-partner functions, where each person has only one other person and there is nobody that's two-timing anybody. It's just kind of the way I think about it. Okay, so a one-to-one function is like a relationship function, meaning that in a true monogamous relationship, it's just you and your other person, and there is nobody that is kind of on the side, if you will, if we're going to put it bluntly like that. All right, so now let's talk about the numerical, graphical, and analytical ways to determine if we have something that is a one-to-one function. So a numerical determination is what we're going to look at first. For this one, we're just going to be looking to see that every x value has only one y value and vice versa. Okay. The graphical determination, a graph must pass both the vertical line test, that's just to see if it's a function, and the horizontal line test. And that will determine if it's one-to-one. Okay? So the vertical line test just tells you have a function. The horizontal line test, what that's doing is making sure that there are no y values that have multiple x values. Because if it were a situation like 2, -3, and 5, -3, if I were to plot those, here's 2, -3, and here's 5, -3. We can see that while it passes the vertical line test, it's a function. It's not one-to-one because both the 2 and the 5 are mapped to a -3, so it's not one-to-one. Okay, it has to meet both conditions. And then, of course, an analytical way to do it. This one's going to be a little more abstract. If there is a point x1, y1 on a graph then no other point will be x2 comma y1. Basically what this is saying is if I have an x value that goes to some y value that we call y1, there will not be another x value that will also go to y1. Okay? All right, so that is how we're going to determine whether we have stuff that is one-to-one. So now let's define the inverse of a function. The inverse of a function is going to be defined as, how do I want to put this? The undoing of a given function and we're going to say it's a reflection over the line y equals x. Okay? So now it says what property of the function must exist in order for the inverse of the function to exist? The given function must be one-to-one because when you do the inverse, it will not have two x values mapped to the same y value. And we'll explore that with some examples in a moment, okay? All right, so now what we're going to do is we are going to look at some examples to determine if the inverse can exist. If the inverse does exist, we're going to give the relation in numerical form. If it's graphical, we'll sketch a graph, and then if it's analytical, we'll give the equation, okay? So looking at my x and my f of x, well, what I want to do first is find the inverse. So to find the inverse, what I'm going to do is figure out, so remember f of x is like y, so we're going to swap the x and the y's around. So we'll have our new x and we'll have what's called f inverse of x. By the way, this f to the -1 is notation for inverse, okay? So I'm just going to take my above table and I'm going to switch the x and the y around. Oops. And when we look at this, now I want to see if my inverse actually represents a function. So looking at my inverse, I have an x value that's mapped to two different y values. So this is not a the inverse is not a function. So f inverse of x is not a function. Okay. If I look at the next one, what I'm going to do is I'm going to, once again, think of this as x and y, so we're going to switch them around. Once I switch them around, I look to see, oh, all my x's are different, so that's good. So therefore, it looks like I have a function. So f inverse is a function. Okay. For the graph, what we're going to do is we're going to swap the x and y's. So this ordered pair here is -2, 1. So I'm going to plot 1, -2. This ordered pair is 2, -1. So I'm going to plot -1, 2. connect those with the segment. This order pair down here is 4, -4, so I'm going to plot -4, 4. And then the point up here is -5, 5, so I'm going to plot 5, -5. And I'm going to use green to really emphasize this graph. And when I use that green, I can clearly see the F inverse exists because the graph is, well, I should say passes the vertical line test. So remember, green is F inverse of X. So the graph passes the vertical line test. I could have tested it just by looking at the original graph, and I could easily see that the original graph is 1 to 1. So another justification would be F inverse exists because F of X is 1 to 1. It's 1 to 1 because it passes the horizontal and vertical line test. Okay. For the graph of g of x, looking at g of x, I can clearly see there are times when the horizontal line test fails. So we would say that g inverse of x does not exist because g of x is not 1 to 1. Okay? You could still graph its inverse, it just won't be a function. So g inverse of x does not exist as a function, but we could figure out an inverse graph for it. And we do that just by swapping x and y again and graphing it that way. Okay, this next one, if we look at the graph, this is a graph that starts and ends here. So h inverse of x exists because h of x is 1 to 1. It passes vertical line test and horizontal line test. Okay, the next one, f of x is this function right here. We should remember our transformations. We go right 3, down 2. And it's a quadratic, so it's going to look like this. And looking at the graph of a quadratic, we can easily see that it fails the it fails the horizontal line test. So it's not 1 to 1. And we would say f inverse of x does not exist. Okay. For equations, this next equation, this is just a line that has a y-intercept of -3 and a slope of 2/5. So it's going to graph like this. So f inverse of x exists because f of x is 1 to 1. So now what I want to do is find the equation for that. So we're going to do a little algebra now. So this is the same as saying y equals 2/5 x minus 3. So what we're going to do is we're going to swap x and y. So we get x equals 2/5 y minus 3. And then we're going to solve for y. So I'm going to add 3 to both sides. Then I'm going to multiply everything by 5 to cancel out the denominator of 5. I'm going to divide everything by 2. Once I do that, I would replace this by calling this f inverse of x equals 5 halves x plus 7.5. Or you could have left that as 15 over 2. And honestly, it doesn't matter. It depends on if you're going to graph it or not. So some people may want that as a decimal to see how it graph. Okay. And now let's look at this one. This is a rational function. I'll do this one and then I will stop and make the second video. Actually, you know what? No, I'm going to pause here and we'll talk about this one because this one's a pretty involved one.